So today's lecture, we're going to talk about transformations that form a key function of the first stage of the graphics pipeline. So the idea is to understand the mathematical basis of transformations. So I will introduce the standard simple transformations and we will derive their matrices. And then we will see how to use these simple transformations to build more sophisticated arbitrary transformations and the corresponding matrices. So finally, I will talk about a trackball interface that is quite useful to specify rotations. The slides also have material on quaternions that are used to model rotations. So this is for self-reading. The reading for this particular lecture is chapter 3 from Angel, and I also have notes on the quaternion that will be available on the Microsoft Teams. So we deal with affine transformations in computer graphics. Like I mentioned, these preserve lines. So what this means is that collinear points get mapped to collinear points. So this is quite useful because the endpoints of the line is what you need to transform in order to implement a transformation of a line. In addition, affine transformations preserve ratios. This is also a useful feature. So almost all the transformations that we care about can be modeled using affine transformations. So for example, they include all the rigid body transformations, rotations, and translations. In addition, scaling transformations are also affine. Shear transformation, which we will see later, are also affine transformations. Affine transformations, like I mentioned, are important in the graphics pipeline. Since we restrict our attention to affine transformations, it is sufficient for us to work with just the endpoints of line segments or the endpoints of triangle primitives rather than describe the transformation of the entire line segment. So in our implementation, what happens is, for example, OpenGL implements the rendering of the line segment. So it takes care of drawing the line segment between our transformed endpoints. So let's look at this by looking at a part of the graphics pipeline. So let's say U and V are two vertices that go in to the graphics pipeline one by one. When they enter the first stage of the graphics pipeline, a transformation T is applied to them. So this transformation is supplied by the application program, the shader, the vertex shader. So U gets transformed to T of U, and later when V enters the pipeline, it gets transformed to T of V. And these transformed vertices, let's say there is a line segment between them, that gets rasterized and displayed on the frame buffer. So what really happens here? We have vertices U and V. After transformation, we know that they get mapped to other vertices T of U and T of V. So here are T of U and T of V. So what we would really like is to draw the line segment that joins T of U and T of V, right? So this line segment is really the transformed line segment UV, right? However, we don't transform the line segment explicitly. Instead, we have just transformed the endpoints. And OpenGL does the job for us and fills in the interior of this line segment. So this is the benefit of working with affine transformations. So note that all we did was to specify the transformations on the endpoints. Now let's look at the various simple transformations one after the other. So let's start by looking at translation. A translation is essentially moving a point P or displacing it to a new location. So this displacement, of course, is specified by a vector. So the new point P prime is given by P plus the displacement vector D. So let's look at the mathematical representation of translation using homogeneous coordinates. Of course, we will assume a reference frame. Let P be the point that we want to displace, and P prime is the displaced point or the translated point. The displacement vector is given by D. You notice that the fourth coordinate is 0. So essentially we have P prime is P plus D. If we write this in the form of homogeneous coordinates, this is essentially an expression in 4D. But this expression is essentially an addition. It's a point plus a vector. What we want is to model translation as a matrix multiplication, particularly using a multiplication by a 4x4 matrix. So we want P prime to be written in this form as TP, where T is a matrix. Right? So this is what the translation matrix looks like. So all I have done here is to rewrite these three expressions. X prime is equal to x plus dx and so on in the form of a matrix T. So the matrix T has 3 arguments. That's essentially the displacement vector, and you see that the 3 arguments appear in the 4th column. So this matrix multiplication based representation is naturally suited for implementation. All affine transformations may be expressed this way, and such a representation is also amenable to concatenation, which is what we will see later. Let's move to another simple transformation, rotation. So here we want to take xy and rotate it about the origin to x prime y prime. Right? We note that the point x comma y subtends an angle phi with respect to the x-axis. So consider the rotation of this point by an angle theta. Right? So x comma y can be written in the angular form, the polar coordinate form, as r cos phi and y sin phi. R cos phi and r sin phi. X prime y prime can also be written similarly with respect to the angle that they subtend, which is theta plus phi. So we can expand this out. The r, note that this remains the same. If we expand the expression, we can rewrite x prime y prime in terms of x and y. So the same works when we rotate about the z-axis. So when I rotate a point x comma y with respect to the z-axis, x prime and y prime are written in the same way as before. Z prime is essentially the same as z. So if I want to write this in homogeneous coordinates, I can think of a matrix R sub z of theta, which is a 4x4 matrix, and we essentially populate it with the coefficients that we get from the expressions here. Just writing it in the form of a matrix, we get such a 4x4 matrix. Notice that this is the rotation matrix where the rotation is about the z-axis, the positive z-axis, by an angle theta. we can imagine that a similar matrix can be written for rotation about the x-axis where the x values are unchanged, and rotation about the y-axis where the y values are unchanged. So the third transformation that I want to talk about is scaling. Scaling essentially refers to expanding or contracting along a particular axis. And the fixed point of this operation is the origin. So what this means is that the origin does not get affected by this operation. We will begin by talking about scaling along the three axes. So this is essentially given by these three expressions. X prime is some scaling factor s sub x times x. Y prime is s sub y times y, and so on. So I can write this in the form of again a matrix where P is the input point which is scaled to get SP, which is equal to P prime, the scaled point. The scale matrix has again three arguments, S sub x, S sub y, and S sub z, which appears in the diagonal of this matrix. So the matrix is kind of clear, I hope. So this matrix takes an object like this and scales it along the three axes. So for example, if in this case, if the vertical direction is the y-axis and s sub y is greater than 1, then I get elongation along the y-axis. And if s sub x, s sub y, and s sub z are less than 1, all three are less than 1, then I get contraction along all three axes to get this object. So this is the scaling operation, scaling transformation. So you may be curious about another transformation, which is reflection. So what is reflection really? Let's look at it in the 2D case, right? So what is reflection in 2D? If I have an original object or an image like this, let's consider it as an object. It's geometry. I would like, so this is a geometric object with various points, and I would like to reflect it. What does that mean? I would like to reflect it about some axes. So let's assume first you want to reflect it about the y-axis, right? So that's x equal to 0. This is as if the y-axis is the mirror, right? And so you're reflecting about that mirror, right? So a point here on this object, let's say x comma 3 gets reflected to negative x comma 3, right? So the y coordinate remains unchanged. The x goes to the negative of x. So this is reflection. So once you write down this expression, you will immediately see that reflection is essentially scaling with negative coefficients. So essentially s sub x is -1 and s sub y is 1. So reflection about the x-axis can be written similarly, and reflection about both x and y-axis can also be written with negative scaling factors. So essentially we have taken care of another important transformation, reflection, by thinking of it as a scaling operation. Let's talk next about inverses. This will lead us towards the development of more sophisticated transformations. We will write down the inverses of the simple transformations we have seen so far just by observing or just by making some simple geometric observations. Translation first. The inverse of a translation, T inverse, is essentially translating by the negative vector, right? So it's T inverse with respect to displacement D is the same as translation by negative D. Rotation by an angle theta, right? So the inverse of rotation by an angle theta, R inverse, is rotation by negative theta about the same axis, right? So this just follows from simple trigonometric observations. Scaling. So let's talk about scaling with respect to a scale factor s, small s. The inverse of this scaling is essentially a scaling with where the scale factors are reciprocals, 1 over s sub x, 1 over s sub y, and 1 over s sub z. Right? So these inverses were easy to write down. So you may want to now check explicitly if rigid transformations indeed preserve lengths. So I will just define what a rigid transformation is, maybe not formally, but here a translation and a rotation are considered rigid transformations. So they are essentially transformations that rigidly move an object to a new position. Now, given that we understand the matrix representation of these rigid transformations, you may want to check that they indeed preserve lengths. So what you have to do is consider two different points, let's say A, B. So this A, B forms a line segment. Consider the transformed version of this line segment. Let's assume that this transformation essentially is either a translation or a rotation, and prove that the length of the edge AB is preserved. It's a very simple linear algebra exercise. Okay, so let's now move on to deriving generic affine transformation matrices by concatenating the matrices that we have seen so far. So the reason we talk about concatenation is that there are two benefits of concatenating the transformations rather than applying the transformations one by one. So in computer graphics, often the same transformation is applied on a large number of vertices. So you can imagine that you have a model which has a few million vertices, and you are trying to rotate this model. So this is essentially means that you are rotating all the vertices inside this model. So the same transformation gets applied to all the vertices. Second, the cost of forming a transformation matrix, let's say M, it could be a concatenation of multiple matrices A, B, C, D, where A, B, C, D could be rotation, translation, or scaling. The cost of forming M is very low compared to applying M on all the vertices. So it makes sense to form the matrix once and then apply it to all the vertices instead of applying the individual transformations A, B, C, D to each vertex P. So the next question that comes up is, in what order do we concatenate? So let's look at a matrix M which is equal to ABC. So if ABC is applied on a vertex P, right, it's clear that the matrix that is on the right is applied first. So for example, so C is applied first, followed by B, and followed by A. Right? So this right to left order is important to understand and be aware of. A question that comes up in this context is, how do I determine the matrices ABC? Of course, I can think of it as transformation, as translation, rotation, and so on, right? But how do I form an appropriate matrix? How do I ask the user what transformation she or he wants, right? So the question here is, how do I form a desired transformation from appropriate specifications? So you may want to think about this. We'll try to give an answer at the end of today's lecture. Let's now talk about arbitrary transformations, beginning with rotation. So here I want to rotate about an arbitrary vector v by an angle theta, right? So the first step, which is what was kind of employed earlier in early days, is to think of this rotation r by an angle theta as a combination of three different rotations about the three axes x, y, z. So these three angles, theta sub z, theta sub y, and theta sub x, are called the Euler angles. So this continues to be used in some disciplines, but there are many disadvantages of this way of modeling complex rotation. For one, the rotations do not commute, so you have to be very careful about what order you apply the rotations. You can apply the rotations in a different order, but the angles will be different. So one has to be very careful about this. What we will do is apply a different approach, which is more intuitive. So let's build this approach one step at a time. First, I want to rotate about a fixed point, which is not the origin, right? So let's say I want to rotate about a point P, right, which is shown here. The way I do this is by first moving that particular point, fixed point, to the origin, perform the rotation that I know how to do, so rotate here, and then move the point back to its original location, right? So what have we done here in each step? So when I move the fixed point to origin, or the origin, I have transformed the entire object. So essentially all the vertices here are transformed by this operation which moves the fixed point to origin. That's a translation. But we know that this is essentially just changing the reference frame, right? So this operation can always be undone at the end by changing the reference frame back to the original reference frame. This is what we do here. That's this pair, right? And once I change the reference frame, it becomes simple to rotate. So I apply the rotation between these two reference frame transformation operations. So this is the idea. So now if I write down the matrices, so remember I have to read right to left. So I first translate so that I move the point PF to origin. So that's why negative PF. Then I apply the rotation. So let's say the rotation here is about the Z axis. So I do the rotation, followed by a translation that brings the fixed point P sub F back to its original location. Let's take this one step further. So now I want to rotate about an arbitrary axis, not just the Z axis. So how do I do this? So what I would do is to first somehow bring this particular arbitrary axis and make it align with one of the axes, right? So in this case, I'm going to rotate this arbitrary axis about the x and y axis so that it aligns with the z axis. So how do I do this? So let's think about this here. So this is the arbitrary axis. I would first rotate it so that the axis of rotation lies on the xz plane. So this is x and this is z. So I'm going to rotate it so that it lies on the xz plane, right? And then I would rotate it so that it aligns with the z-axis. So the first rotation, if you see this first rotation, I think the arrow points in the other direction. That's because it's talking about how to rotate to get here. So imagine that you are rotating it in the opposite direction. So this is your axis and you're rotating it about the x-axis. You're rotating this vector about the x-axis so that it falls onto the xz plane. And next you rotate it about the y-axis. So you rotate it above the y-axis so that it aligns with the z-axis. After this, you apply the rotation that you wanted to in the first place. And then you reverse all the axis aligning rotations. Right? So the matrices look like this. You first apply a rotation about the x-axis, followed by a rotation about the y-axis. Then you apply the rotation that you actually wanted to, followed by the rotations that will reverse the axis alignment. The question remains, how do you find theta x and theta y? Right? So recall that I don't have to apply these rotations one by one. I would just concatenate all of them to form a single matrix. So recall that we still have not figured out how to compute theta x and theta y. Right? This is not too difficult. So let's look at this. So here is my vector v shown in blue here. This can be represented in many ways. One way to represent it is by looking at the endpoint alpha x, alpha y, alpha z. The other is by looking at the angle that this vector subtends with respect to the three axes. So these are the phi x, phi y and phi z. Right? If I assume that the vector is a unit vector, then I know that how the alpha x and phi x are related, essentially by cosines. So that's why they are called direction cosines. So the rotations that we talked about are here. So first, the vector v is rotated about the x-axis. It's rotated about the x-axis by theta sub x, right? So now what is theta sub x? If you look at the projection of this rotation, you will see that the unit vector gets projected to this blue arrow here, whose length is d, right? And this angle is theta x. So you can write down cosine and sine of theta x in terms of alpha y, d, and this length, which is essentially alpha sub z. So next, theta y. So once this vector gets rotated onto the xz plane, you have this blue vector here, and remember it's unit vector, and you are rotating it to align with the xz axis. You can again write down the expression for theta y, because you know that this length is d, and this is a unit vector, and you know that this is alpha sub x. So you know what cosine and sine of theta y are. Since I know the cosines of and sine of theta x and theta y, I can write down the two matrices R sub x and R sub y. So we are done with that. So what we have done now is to write down the expression for rotation about an arbitrary axis V. And in addition, we know that this rotation need not be about the origin. We know how to solve that problem also via a translation. Right. So let's put these together. So typically when you want to model an object, so let's say I want to show this apple in the scene, right? I have to apply some transformations. The apple lies in my inventory. So I often start with a generic object, the apple, which lies in its own inventory. It is centered at its origin, such as here. It is oriented along its own axis, such as here, and it comes in some standard size. I want to create an instance of this object in the scene. So for example, my scene could have 10 different apples at different orientations, different sizes, but I have one sample in my inventory. So what I do is I create multiple instances of this apple, and the way I create these instances are by applying an instance transformation. So this instance transformation is a scale first, followed by rotation. So notice that this rotation is simple because it's about the origin. And then I apply a translation, which is a location, a locate. So the scale, orient, locate will help me place this apple in the scene. So the matrix that I have here is M, which is TRS, scale first, then rotate, then translate. So in your graphics program, as a good programming practice, you may want to apply such an instancing transform to every object. So we are almost done with our discussion on transformations. I just want to cover the shear transform to finish this discussion. Shear is also a basic transformation. So this is essentially a transformation that pulls the top and bottom faces of this cube, for example, in opposite directions. So the top face gets pulled along the positive x, and the bottom face gets pulled along the negative x. So these are so you can imagine that this is the result of the cube being pulled apart by anti-parallel forces, essentially a shear force. So the operation can be written as follows. So for points that lie above the xz plane, a point xy gets pulled in the positive x direction to x prime y prime. So this can be described by an angle theta, the shear angle. And if you want to rewrite this, y and z, remember, are not changed. X goes to x plus y cotangent theta, right? So this can be written in the form of a matrix. So that is h of theta. So essentially h is just writing down these three expressions, right? So we will not talk more about shear matrices now. We will come back to this later when we try to talk about generic projections. Let's close the discussion by talking about transformations and how you want to specify them. So as you have done, so in your lab tasks, you have specified matrices explicitly. To make your code modular, you may want to create functions, let's say translate, rotate and scale. So these are defined by you. You may want to design these functions and implement them such that they create the corresponding transformation matrices, and then you can accumulate these transformations. So this is completely up to you. So left to the user for implementation. So the question that I posed earlier comes back again. Given that I want translation, rotation and scaling, I know how to write down the matrices. But the question is, how does the application specify these transformations? Of course, I can specify it by writing down the displacement vector or specifying the angle of rotation and the axis of rotation. But these are not very intuitive. The user may want to specify transformations via example. They may want to say that this vertex, take it from here and move it to here, or this particular cube rotated by in this particular way, right? So the question is, how do they specify these transformations? Let's see an example for rotation. So the example is via this construct called the virtual trackball. Let's see what a trackball is first. A physical trackball is essentially an upside down mouse. So in the older generation of mouse, you had a rolling ball in the bottom of the mouse. This would roll as you move the mouse on your mouse pad, and it will determine the position of the cursor on the screen. Now an upside down mouse is just looking at the ball that's rolling, and now you have access to the ball. You can touch it here and roll it, right? So in that sense, it's an upside down mouse. Let's assume further that this ball has no friction, so it rolls freely. So essentially, if you push the ball, it will keep rolling in that direction. So if I have to use this upside down mouse, there are two modes of operation. One is you continuously hold with your hand. You can hold this ball and move it in some direction. The other is you can push it in some direction, like push it like that in some direction, and it keeps spinning. So let's say I have a mouse, a regular mouse, and I want to somehow implement this trackball. So I want to emulate both behaviors, the two behaviors that I talked about, using a simple mouse. Of course, we want to ask why. Why do I need a trackball? So the answer is that if you can imagine that your object that you are seeing on the screen lies inside the trackball. So imagine that the trackball is like a sphere, and your object lies inside the trackball. In order to manipulate your object, you can imagine that you are holding the trackball and you are rotating it like you would rotate the sphere or a globe. And by doing this, that same rotation is applied on the object which lies inside the sphere. This is very intuitive. This is as if you are taking the object in your hand and moving it around, rotating it to have a better view. Okay, going back to our question, we want to emulate the behavior of the trackball. So we will solve this in two steps. First, by mapping the trackball position to the mouse's position, and we will get the appropriate modes using whatever toolkit or windowing library that we use. So here is the frame for the trackball, the XYZ, and the origin is at the center of the trackball. So note that what you see here is only the top part of the trackball, right? It's only the hemisphere. Let's position that mouse pad. So here is the mouse pad. The XZ plane is the mouse pad. So the mouse pad is the XZ plane. So both the mouse pad and the upper part of the ball are 2D surfaces, right? So you can project points from the mouse pad to this surface and vice versa. You can reverse that projection also, right? So this is what we will do. We will take a point on the mouse pad XZ, right, and consider the point on the trackball that corresponds to this. So the way you get that point is by projecting directly up. So you go from XZ to XYZ, and the Y coordinate is essentially given by the radius of the trackball, the sphere. So it's given by under root r squared minus x squared minus z squared, right? Of course, this expression is valid only if you are considering xz that lies inside the hemisphere. Let's go back to this projection. So you have a point here that comes from the mouse pad, and you project it up onto a point on the hemisphere, right? So P1 is the starting position and P2 is the terminating position. So if I move the mouse from here to here, right, I can imagine that this is the same as taking the point P1 or holding the trackball at P1 and rotating it till such that the point goes all the way to P2, right? So the rotation that is given by this mouse movement on the mouse pad is equal to P1 rotating towards P2, right? So what is the angle of rotation? It's essentially the angle subtended by the vector given by origin to P1 and origin to P2, right? So the angle between these two vectors is the angle that we want for the rotation. And what is the axis of rotation? The axis of rotation is essentially the cross product between P1 and P2. So we have the axis of rotation and we have the angle, so we can write down the rotation matrix. So this is how we specify rotations and form the corresponding matrix. Quaternions are extensions of complex numbers. So these are called hyper-complex numbers. They are very useful to model smooth rotations, and particularly for animations. So I have included slides that talk about these quaternions, and I also have some written notes that I have uploaded on Microsoft Teams. I'll ask you to look at that to get a better understanding of quaternions.